Welcome everyone. Let's begin our lesson for today by going over the learning goals and success criteria. First, what are we learning? We're learning how to recognize all numbers as being part of the number system, to determine which number set within the number system a number belongs, to recognize that numbers can belong to multiple number sets at the same time, to recognize closure of number sets within the number system under mathematical operations, to recognize the relative position of rational numbers on a number line, to compare rational numbers and order them from least to greatest, to find the exact location of a rational number on the real number line, to use the location of rational numbers in order to find the location of 1 on the real number line, to convert decimal values including repeating decimals to fractions, to convert fraction values to decimals, to formulate logical mathematical arguments in order to prove mathematical principles, to prove the closure of rational numbers under mathematical operations, to recognize that all real numbers can be factors of all other real numbers, to recognize that numbers do not have to divide evenly in order to be considered factors, to critique the work of others and examine multiple methods and techniques to solve problems, to determine the best course of action when completing problems and recognize that it is important to have multiple techniques to solve a problem, to determine the placement of various numbers on the real number line, to find the relative position of real numbers that are undergoing mathematical operations. How are we learning it? Through the Reasoning with Rational Numbers review notes and the Reasoning with Rational Numbers review assignment, as well as the Reasoning with Real Numbers review notes and the Reasoning with Real Numbers review assignment. When can we use this information? To perform simple calculations such as a budget by recognizing boundaries of numbers to determine if adding the items in your budget will stay within your income amount. To cut boards into smaller equal pieces in order to create or repair furniture. To organize thoughts and ideas about any topic in order to provide a valid argument for your thoughts, beliefs, and ideas. To recognize that there are an infinite number of solutions to every problem and that the most important factor in solving any problem is to find the best approach. To organize thoughts and ideas about a topic in order to provide a valid argument for your thoughts, beliefs, and ideas. And to organize thoughts and ideas according to a given structure, such as planning out the events of a day based on time, duration, and number of tasks. How do you know you learned it? By getting a score of 4 on the Reasoning with Rational Numbers review assignment and a 4 on the Reasoning with Real Numbers review assignment. Now let's take a look at our agenda for today. We will begin by going over the learning goals and success criteria. While we do that, you'll fill out your Get It Started. Once you've completed your Get It Started, we'll go over it together and answer any questions that you may have. Next, we'll do our weekly raffle. After that, we'll go over the Reasoning with Rational Numbers review notes and the Reasoning with Rational Numbers review assignment. Once you've completed your Reasoning with Rational Numbers review assignment, we'll go over it together and answer any questions that you may have. At the end of class, we'll go back over our learning goals and success criteria while you fill out your Before You Go. Your only homework for tonight is to work on the Reasoning with Real Numbers review assignment and any incomplete assignments that you may have. Let's take a look now at the Reasoning with Rational Numbers review notes. The notes begin with the learning goals and success criteria. First of all, what is a number line? A number line is a line on which numbers are marked at intervals used to illustrate simple numerical operations. So for instance, here's 0, here's 1. This number line in particular is called the real number line because it represents all the real numbers. Now, let's talk about location. So the difference between exact location and approximate location. So the exact location of a number on a number line requires a compass and straight edge to find and is in direct proportion to the unit length. So we know exactly where it is. Approximate location on a number line does not require tools and is an estimation. So it would be like saying we're splitting this check and everyone just put in $20. That's approximate. An exact version would be something like we're splitting this check, everybody owes $19.85 or something like that. So that's the difference between the exact location and approximate location. So we're given this unit here. So this is the number line. We have 0 and 1, and we're going to try to plot 1/2 on the number line. Well, what we're going to do is we're going to kind of eyeball this. We are told that we're looking for the approximate location, so it doesn't have to be exact. So it should be somewhere in here. So 1/2 is between 0 and 1. So we're going to take that 0 and 1, and we're going to go about halfway through that. So we're going to break that into 2 equal pieces. Is that exactly equal? I don't know, but it's close. So we're going to go ahead and move our dot to that point here on the number line. So right about there should be 1/2. Is it exactly 1/2? Probably not, but it's pretty close. Now what about 1/3? Same thing, we're looking for the approximate location. We should note that 1/3 is between 0 and 1. So we're going to start with 0 and 1. And then we're going to break this into 3 equal pieces because the denominator is 3. So we're going to break it into 3 equal pieces. So there's my 3 equal pieces. Are they exactly equal? Maybe not, but close. And then we're going to go ahead and drag our point to that location, which is here. This is 1/3. So right there. Now what if the number's bigger than 1? So we have 5 halves. Well, again, we're finding the approximate location. We should note that 5 halves is between 2 and 3 because this is really 2.5. So we're going to copy 0 to 1 out and extend it from 1 to 2 and then 2 to 3. So there's the distance. We're going to copy it over here. So that should be a 2. And again, that should be 3. So now this is between 2 and 3, which is where we said this is. So now we're going to cut that area between 2 and 3 into 2 equal pieces. So right about there. So that should be about 5 halves. Again, is it exact? No, but it's a pretty good approximation. Now what if we're asked to plot a negative number on the number line? Well, this is -3 halves. We want the approximate location. We should notice that -3 halves is between -1 and -2 because this is really -1.5. So we're just going to take this distance from 0 to 1 and copy it towards -2. So we're going to copy it over here. That would be -1 and again would be -2. So I take that distance and copy it over. Now here's -2, here's -1. So we're right, it should be right in here somewhere. So we're going to cut that part into 2 equal pieces because the denominator is 2. So we cut that into 2 equal pieces, right there. And now we can say that the point should be right about here. That should represent -3 halves. There's a video here that you can watch on how to check positions on a number line using Desmos. Let's talk now about how to check the position of rational numbers on a number line. So first we're going to go to desmos.com and we're going to click on Graphing Calculator. Now notice it forms a graph here. It's not exactly a number line, but if we look at just the x-axis, that is a number line. So what we're going to do is we're going to put in our values. So let's say we're trying to check where 3/4 is on the number line. So we're going to put 3/4, comma, 0 in parentheses. And notice it ends up exactly on the x-axis. And we can see it's close to 1 right here, but not quite there. So I can label that and check it. Let's say we want to check something else, maybe -5/7. So that's what we want to check, and we're going to go ahead and put it in parentheses, comma, 0, and we could check it here and see exactly where it is. So we can check the relative positions of these rational numbers and find their exact locations using this, and we can use this to check our work when we're doing our relative positioning. Now let's talk about the definition of infinite set closure. First of all, what does infinite mean? Infinite means an uncountable number of elements. So it goes on to infinity. It keeps going forever. So an example of this would be like the natural numbers. So we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we can keep counting. And no matter what number we stop at, there's always a number past it. So that's an infinite number of elements. Therefore, an infinite set means that we cannot count the number of elements in the set. The opposite of this would be a finite set in which there are a countable number of elements. So let's say I wanted the natural numbers between 1 and 10. Well, that goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and stops. And we can't keep going. So that would be a finite set. So an example of an infinite set would be the set of integers. So there's no limit to the number of integers we can count. Now, closure definition. What does closure mean? Closure under an operation means a set is considered to be closed if when that operation is performed on any two elements within the set, the result is also in the set. Okay, note that
this must be true for all elements in the set. If there is even one case where the result falls outside the set, then it is considered to be not closed. Okay, so let's take a look at what this means. So here's an example. We have the set of -1, 0, and 1, and want to know, is it closed under addition? So what that means is I'm going to take each of these elements, so like -1 and 1, and when I add them together, I get 0, which is in the set. So that means that the set might be closed. If for some reason, though, I end up adding two numbers together and the result is outside the set, so let's say I add something together and I get 6. Well, 6 is not in the set, so therefore it is not closed. So an example of what would make the set closed would be -1 plus 1 equals 0. Because 0 is in the set, it looks like it might be closed. Now, is there an example we can come up with that makes it out of the set? Well, if we add 1 plus 1, because we do need to include it plus itself, so 1 plus 1 equals 2. Well, 2 is not in the set, therefore the set is not closed. And again, if there's even one example of this, so it doesn't matter that this part ended up inside the set. Because this one example is out of the set, then the whole set is not closed. So now let's take a look at this infinite set here, the set S of integers, and we want to know, is it closed under addition? Now we can't use a table anymore, so we need to think of some examples of addition of integers and then try to broaden it and say, is there any way that any two integers can be added together and not be an integer? So we do some examples here, and we can see that they're still turning out to be integers. So is there any way we can add two integers together and not get an integer? So if I add any two negative integers, is there any way to get a fraction out of it? Is there any way to get a real number out of it? Is there any way to get a complex number out of it? Well, no, there's not, right? Anytime I add any two whole numbers together, I should get another whole number. So therefore, there is no way to add two integers together without getting another integer, so therefore the set is closed. Now what about this? The set S of integers closed under division. So again, we're going to think of some examples. So we have 2 divided by 1, 1 divided by 2. Notice here though, when we do 1 divided by 2, we get 1/2. Well, 1/2 is not an integer, that's a rational number. So therefore, when we do it that way, we know that it's not closed. Now, there's an easier way for us to be able to tell that this set is not closed. Because I told you last time, if we include 0 in the set, then it is never closed under division because it's undefined. So if we divide something by 0, it will always be undefined. So 0 is an integer, so if we were to divide a set by 0, it would be undefined. So therefore, that previous set would not be closed because of division by 0. Now, what if we said the set of rationals excluding 0 is closed under division? Well, again, we're going to think of some examples. So we have 1/2 divided by 1/4 is equal to 2, and -1/2 divided by 1/3. Remember, really, it's just multiplying by the reciprocal. So is there any way we're going to get something other than a rational number, other than a fraction? Well, we keep thinking of some examples, and when we keep looking, we can see that there is no way, and we did exclude 0, so we know that 0 is not an issue, so we don't have to worry about dividing by 0. So therefore, we can just look at these examples and continue to come up with more examples, and we can see that the set is actually closed because no matter what, when I divide two fractions by each other, I will always get another fraction. Now, here are the steps for finding the exact locations on a number line. First, we construct a line between the 2 points and label the points 0 and 1. So we need to know where 0 and 1 are. Then we're going to construct a line through 0 that is a transversal to the first line. So it's going to pass through 0 and work upward or downward, either way. Then we're going to use a compass to create equivalent circles on the transversal line. The number of circles should be equal to the denominator of the rational number we are trying to find. And then we're going to connect the point from the center of the last circle to the point labeled 1, and we're going to copy that angle to the center of the circle that matches the numerator of the rational number we are trying to find. Well, what exactly does that mean? Here are some examples of what we're going to be doing. So there's a video here that shows you how to construct a rational number on the number line. Let's take a look now at how to construct rational numbers on the number line. So we're given 0 and 1, and let's say we wanted to construct something that comes between them. Let's try maybe 2/3. Okay, so what we're going to do is we're going to use the ray tool and construct a ray that goes from 0 and extends out somewhere around here. And then we're going to break this up, and let's say that the number we're trying to come up with is 2/3. So first thing we need to do is we need to break this line up, this ray up, into 3 parts. So let's go ahead and do that. So we're going to go to where it says circle. So we're going to use the circle tool, and we're going to click here and extend it out. We can go as big or as small as we want, but the bigger it is, the more difficult it is to work with. So let's just go ahead and keep it nice and small, maybe something like that. So there's my first circle. Now I need to copy this circle and use this as my center. So I'm going to do the same thing, but this time I'm going to go to where it says segment. I'm going to click on this point and this point. That'll give me that radius. Now I can use the compass tool to copy it. So I'm going to click on compass. I go to more tools, compass, and I'm going to click on the segment I just created, which is the radius. It gives me a circle. Notice if I place it on this one, it should be the exact same size. And I'm going to do it again. So now there's 1 point. Then I'm going to do it again. So I'm going to click on this radius. And there we go. There's 2 points. And again. And there's 3 points. So now I have 1/3, 2/3, and 3/3. Now the next step is I'm going to connect 3/3 to 1 because 3/3 is equal to 1. So I connect those. And I wanted to find where 2/3 was. So all I need to do now is create a parallel line to this one through this point. So I'm going to go ahead and do that. I'm going to go to where it says more tools. I'm going to click on parallel line. And I want it to be parallel to this line here. So I'm going to click on that. And then I'm going to bring it. And I want it to go through this point right here. So I click on that. Notice this line intersects the number line right here at this point. So I'm going to go ahead and put a point. I'm going to click point and put a point right there. And that point should represent exactly 2/3 if this is from 0 to 1. Here is another video that shows you how to construct a rational number on a number line. Let's talk now about how to graph rational numbers on a number line. Let's say that this time we want to find negative 2/3. Well, we know negative 2/3 is going to be over on this side over here. So what we're going to do is we're going to construct 2/3 on this side and then copy it over to the other side. So just like before, we're going to start with our ray tool. We're going to click on this point and extend it. Then we're going to break this ray up into 3 parts and connect the third one to 1. So we're going to use our circle tool and go from here to here. And then we need to get this radius so we can copy it. So I'm going to use the segment tool to click on this point and this point. That gives me the radius. Now I can go to more tools, compass, and click on that radius right there. So I clicked on it. And now I have another circle. It's exactly the same size. And I'm going to place the center of it right here at this point. So I'm going to go ahead and do that. Then I'm going to do it again. So I click on this radius again. Now I have 2 points and click it again. And then I'm going to do, now I have a third point. Now I can go ahead and use my segment tool to connect it because it's 3/3. So there we go. Now I can go ahead and use my parallel line tool. So I'm going to click on more tools, parallel line. I want it to be parallel to this one and to pass through here. So I click on that. Now notice I have a point where they intersect right here. That is exactly 2/3. But we wanted negative 2/3. So in order to get negative 2/3, I need to just create a circle that goes from here to here. So I'm going to use a circle. I want this to be my center and this to go out to here so that my radius is 2/3, which means that on the other side it's also 2/3. So over here, this point should be exactly negative 2/3. And here is one more video that shows you how to construct a rational number on the number line. Let's talk now about how to graph rational numbers on the number line. This time we're going to take a look at a number that's bigger than 1. So let's say we want 5/4. So what we're going to do is we're going to use our ray tool and draw a ray that goes from 0 away from it. And now we're going to go ahead and take the bigger number of the fraction. So in this case it was 5/4. So 5 is the bigger number. So that's how many circles we're going to draw. So I'm going to use the circle tool and click here, something like that. And I need to copy this 4 more times. So I'm going to go ahead and use the segment tool here and here. That gives me the radius. Now I can copy the circle. So I'm going to go to More Tools, Compass. I click here. And I'm going to place the center of it here. So there's 1 point. I do it again, 2 points. Again, 3 points. Again, 4 points. Again, now we have 5 points. 1, 2, 3, 4, 5. So now what we need to do is we need to connect 4/4, which is 1, 2, 3, 4. So 4/4 connects to here. So I'm going to go ahead and use the segment tool to connect this point with this point. And now I need to do a parallel line to this through 5, through the 5th one, so because that would be 5/4. So let's go ahead and do that. So I'm going to use More Tools, Parallel Line. I'm going to click on this line here. And now I want to bring it up and place it right here at that point. So now we should notice that we have a parallel line and it crosses the number line right here. And this point here where it crosses should be exactly 5/4. So I'm going to go ahead and put a point right there, and that is exactly 5/4. Now, what does it mean to find the unit length? Finding the unit length means that we're going to find where 1 is. So in this case, we're given where 0 is and 3/5, and we need to know where 1 is. So here's a video that shows you how to find the unit length, or 1, on the number line. Let's talk now about how to find a unit length on the real number line. So what we're given here is we're given 0 and 3/5, and the unit length, another way of saying that is we need to find where 1 is. So if this is 0 and this is 3/5, then 1 should be out here somewhere. So here's how we do it. We're going to do it very similar to the way we found our rational numbers on the number line. So we're going to go ahead and use the ray tool. We're going to start at 0 and go and work away. And we're going to take the bigger number, which in this case is 5. So we're going to cut it into 5 pieces. So we're going to use the circle tool. Extend it away. So there's my first circle. Now I need to use my segment tool here and here to create the radius. Now I can copy that circle. So I'm going to go to More Tools, Compass. I'm going to click on this segment. This gives me a circle, same size. I'm going to go here to the center. So now I have 1 point. I do it again. 2 points. 3 points. 4 points. And 5 points. So there's my 5th point. So this is 3/5. So I'm going to connect the third one, 1, 2, 3, to here. Now if I do a parallel line to that through the 5th one, that should be 5/5. So let's go ahead and do that. So we'll use the parallel line, and we want it to be parallel to this segment here. So now it goes exactly the same angle, and we want it to go through this point here. Just like that. Now if we notice, this line that we just created crosses the number line right there. So we're going to go ahead and put a point where they cross. And that point right there should be exactly 1, or 5/5. Here's another video that shows you how to find the length of a unit on the number line. Let's talk now about how to find the unit length on a real number line. So in this case, we're given -1/2 and 0.
and we're asked to find the unit length, which is 1. So what we're going to do is we're going to go ahead and find -1 since we're already on the negative side, so we're going to go draw it this way. We'll find -1 and then copy it over to the other side. So we'll go ahead and use our ray tool, and we're going to draw our ray going this direction towards the number that we know. So we start at 0 and go this way. Now from there, we're going to go ahead and draw a circle, and we take the bigger number, which is 2, so we're going to cut this into 2 parts. So let's go ahead and do that. So we're going to use the circle tool, something like that. Now we're going to use our segment tool here to connect these 2 points and get our radius. Now we're going to go to More Tools, Compass, and click on that segment. That gives me a circle that's the same size. We're going to do that. We have 1 point now, and we're going to do it again. So we click this segment, connect that. So there we go. So now we're going to go ahead and use the segment tool to connect 1/2, because this is 2 parts, so half of that is here. So we're going to connect that to there. And we're going to draw a parallel line over here, and that should give me the exact location of -1. So we're going to go to More Tools, and we're going to click on Parallel Line. I want it to be parallel to this one, and I want it to pass through this one here. So I click on that, and notice I have a point where the 2 lines intersect right there. That should be the exact location of -1. Now I just need to copy it to the other side. So I'm going to use a circle and go from this point to this point. That gives me a radius of -1 here, or just radius of 1, which means that on the other side the radius is also 1. So I'm just going to put a point where they intersect right there, and this point here should be exactly 1. And here is one more video that shows you how to find the length of a unit on the number line. Let's talk now about how to find the unit length on the real number line. So in this case, we're given 0 and 5/3, and we're expected to find the unit length, which is 1. So just like before, what we're going to do is we're going to use our ray tool and click a point here at 0. Go ahead and extend it. Now from there, we're going to break this up. The bigger number is 5, so we're going to break this up into 5 circles. So we're going to go ahead and do that. So let's go ahead and click on Circle tool. And we're going to extend it, make a circle here. So we have 1 point there. Now we're going to go ahead and do it again and again, right? So first, before we can copy it, we need to do the segment tool and connect this point with this point. That creates our radius. Then we can use the compass to copy this. So we're going to use the compass tool and click on this. And there, now we have 1 point. We do it again. 2 points. Again. 3 points. 4 points. And 5 points. So now we can match 5/3 with this point here. So let's go ahead and do that. So we're going to go ahead and use the segment tool to connect this point and this point, because that's 5/3. Now if we draw a parallel line to this line here, going through 1, 2, 3/3, that should be exactly 1. So we're going to go ahead and do that. So we're going to use the parallel line, and we want it to be parallel to this one, and we want it to pass through 1, 2, 3 right here. And notice now the line we just drew intersects the number line right here. So we're going to go ahead and put a point. That should be exactly 1. Now we're given a number line here, and it says how many rational numbers exist between 2 numbers. So how many values can we place between 0 and 1? Well, we can do like a half, right? That would be 1. Then we could cut that in half. That would be a 1/4. Then we could cut that in half. That would be an 1/8. Then we could cut that in half, and it would be a 16th. Then we can cut that in half, and it would be 1/32. Is there any limit to the number of times we can keep cutting that in half? And even at that, we could go 1/6, 1/3, 1/12, and so on. So we can do this with any values. And then on the other side, we can go 2/3, 2/6, 4/6, 5/6, etc. So if we were to cut it in half and place a point at 1/2, how many values could we place between 0 and 1/2? This is known as a midpoint strategy, where we keep cutting it in half like I just mentioned.
What other ways can we use to find rational numbers between two other numbers? Well, we can use any number of ways. What we should come out of this knowing is that there is no limit to the number of rational numbers between two values. So even if I pick two rational numbers, 1/3 and 1/2, there's still an infinite number of values that come between them. So now, who is the greatest of them all? We have 3/5 is greater than 5/6, and we need to determine whether that is a true statement or not. So if the denominators are not the same, how can we determine which is the greater rational number? Well, one answer is we could get common denominators. So I could change this to be over 30 and this to be over 30 and then see what our answer is. That's a lot of work, but that is a possibility. We can cross multiply. So 3 times 6 is 18, so this one's equal to 18. 5 times 5 is 25, so this side is greater. We could also convert to a decimal. So I can change 3/5 to a decimal and 5/6 to a decimal. I can plot them on the real number line using Desmos. So I could put in 0, 3/5 and 0, 5/6 and see which one's further along. And lastly, I can compare to other rational numbers to determine the distance. So let's say, let's try to figure out if these are comparable. If one's bigger than 1/2 and the other one's not, well, then we know that the one that's bigger than 1/2 is the greater number. So those are some examples of what we can do. So common denominators, that's one possible solution. So we have 3/5 and 5/6. Well, we can see that our common denominator should be 30, right? Because we multiply this by 6 over 6 and this by 5 over 5. And what we end up with is 6 times 3 is 18 and 5 times 5 is 25. So we get 18 over 30 and 25 over 30. So that's one possibility of what we can do. Now, cross multiplication. Cross multiplication is just like finding the common denominator, except we don't worry about the denominator itself. So we're just going to multiply 3 times 6 and 5 times 5. And we end up with 18 and 25, which we know that 25 is greater. Next, we can convert to a decimal. So we have 3 divided by 5, which is 0.6, and 5 divided by 6, which is 0.83 repeat, which we can see that this number is greater. Next, we can plot these on the real number line. So if we do that using Desmos, we plot 3/5, we should end up with something that looks like this. This is our point for 3/5. And then if we do 5/6 as well, we end up with a point right here, and we can see that this one is greater than this one. Lastly, comparing it to some other rational number. 3/5 is close to 1/2 because 2/5 is over 5 is equal to 1/2. 5/6 is not as close to 1/2 because 3/6 is 1/2. And we have 5/6, so we're much further away here, so we can see then that 5/6 must be bigger. So these are different strategies that you can use to compare rational numbers.
Now, what is a rational number? A rational number is any positive or negative number that can be written as a fraction. Notice that a fraction is considered to have both a numerator and denominator that are integers. So an example of this would be 2 over 3. It can't be 2.5 over 3 or pi over 3. Those would not be considered rational numbers. So it's got to have an integer in the numerator and an integer in the denominator. That's the definition of a rational number. Now, what is a proof? A proof is a logical argument that shows that a statement is true. So you'll be given a statement, and you will have to decide if that statement is true or not. And if it's true, you have to be able to prove that the statement is true. And to do this, we'll be using a 2-column proof. So on the left side, we have our statement, and on the right side, we have our reasons. The statement is the claim that we are making. It should always begin with whatever information is given. Then we will continue into the information that we decide based on the given information. So statement is basically what we know. The reason is a mathematical justification for the claim. These have to be proven mathematical theorems or definitions that we know to be true. So we can't just say it's true because we say it is, or because we think it is, or something like that. It has to be a proven theorem or definition that allows us to state that that is the case. So what does it look like? This is an example of a two-column proof. So we have our statements over here. A over B plus C over D are rational numbers. That's a given information. So always we'll begin with our given information, which means the information that they actually tell us. From there, we start coming up with other things. So we can say that this is A over AD over BD plus BC over BD. How do we know that? Well, all we did there was to get from here to here, we found common denominators. And that's the definition of common denominators, right? That's something that we know to be true. So we use definition of common denominators to be able to add these two rational numbers, even though they don't have common denominators already. After that, we have that AD, BC, BD are all integers. So this is an integer, and the denominator is an integer. And the reason we know that is because we've already proven during our last unit that integers are closed under multiplication. So we know that because they're closed under multiplication, then A times D, as long as these are both integers, the result will still be an integer. Then we can go ahead and group these. We leave the denominator as BD, and then we add AD plus BC. And that's just the addition property of fractions. We know that when we do this, we just add those two numerators together and leave the denominator as it is. Now we know that AD plus BC is an integer. This plus this will be an integer. And we know that because we know that this number and this number will be an integer because of the addition property of fractions. We know that this number and this number will be an integer because we know that integers are closed under addition. So if I add any two integers together, I get another integer. So now, if this is an integer up here, the result of up here is an integer, and the result of down here is an integer, then it becomes a rational number. So that is just the definition of a rational number, because the definition of a rational number, as we stated earlier, was that the numerator is an integer, the denominator is an integer. So notice that every statement has a reason, and every reason is a proven mathematical concept that we've already learned. It's not something that we haven't learned yet. It's everything in there is stuff that we've already learned. And notice that we started with the given information and worked through to the conclusion. So we're going to actually do this proof now. So we're given that two rational numbers, and we're expected to prove that rational numbers are closed under addition. So this should always be how it starts. A over B plus C over D are rational numbers. It should always start that way. Now, the operation may change. If we're doing subtraction, then this would be A over B minus C over D. If we're doing multiplication, it would be A over B times C over D. But no matter what, we start with this. And that's given information, right? We're told that they're rational numbers, so that's given. And all we did was break it down and write them as A over B and C over D. Now we should note that A, B, C, and D are all integers, and we know that because of the definition of a rational number, right? Because these are rational numbers, that means that each of these have to be integers. Now, from that, we need to decide how can we actually add these together? How can we add A over B plus C over D? Well, we should notice that they don't have common denominators. This one's B, this one's D, so we need to create common denominators. So in order to do that, we need to multiply both the top and bottom here by D and top and bottom here by B. And we should end up with A over D times B over D. And we should end up with AD over BD plus BC over BD. And all we did there was find the common denominator. So that's definition of common denominators. Now from that, we need to be able to recognize that AD, BD, and BC are all integers. And how do we know that they're integers? Well, because we know that integers are closed under multiplication. So that's our reason. So we know that this is an integer, this is an integer, and this is an integer. So far, even though we change these and have common denominators, we haven't changed the fact that we have rational numbers. We're still adding two rational numbers together. Now we're going to go ahead and combine the numerators just like we would with addition of fractions. So we have AD plus BC, and the denominator stays the same, which is BD. And that's just the addition property of fractions, right? We just add, the addition property of fractions says we add the numerators and leave the denominator as is. Now the question is AD plus BC an integer? Well, it is an integer, and we know that because of integer closure under addition. So anytime we add two integers together, we know that we end up with another integer. So we already stated that this was an integer and this was an integer. We add them together, we get another integer. So that means that this part up here and this part down here are both integers, which means that it's a rational number. And the reason for that is just definition of a rational number. Remember, a rational number definition says that the numerator is an integer, the denominator is an integer. We proved that this is an integer and this is an integer, therefore it is a rational number. Now let's look at an example for multiplication. So we're given that we have two rational numbers, and we're expected to prove that rational numbers are closed under multiplication. So we're going to start with A over B times C over D, and we're going to state that those are rational numbers, and that's given to us. Now we should note that A, B, C, and D are integers, and we know that they're integers because we're given that these were rational numbers. So if they're, by definition of rational numbers, that means that the numerator and denominators each have to be integers. So our reason for that would be the definition of a rational number. So now we're going to go ahead and multiply A over B times C over D. And that's given, right? That's what we're told to do, is multiply them. Now from that, we're going to go ahead and multiply. We know that by definition, we're going to multiply directly across. So we get A times C and B times D. And that's just the multiplication property of fractions. Now, we need to determine, are AC and BD, are those integers? Well, we're multiplying an integer times an integer, so we know that by the integer closure, we know that when we multiply two integers together, we always get another integer. So, and that holds true for both the numerator and denominator. So therefore, AC and BD are integers because of integer closure under multiplication. Now from that, we can say that AC over BD is a rational number because of the definition of rational numbers. Because if this is an integer and this is an integer, then the result is a rational number. Here are some theorems and definitions that you'll need to use for your assignment. Given, definition of common denominators, the addition property of fractions, subtraction property of fractions, multiplication property of fractions, the reciprocal property of division, integer closure under addition, integer closure under subtraction, integer closure under multiplication, and definition of a rational number. So everything that you need for your proofs are on this slide. Let's take a look first at fractions. So think of fractions always as division. So therefore, 1/2 is the same thing as 1 divided by 2. So if we wanted to divide this, we would just put it into our calculator and divide 1 divided by 2, and we get 0.5. We could also use long division to find the decimal value. So we could say 1 divided by 2. So I put this as 1.0 because I know that 2 can't go into 1, so I know I'm going to have to include a decimal point here. So now I take this and say, how many times does 2 go into 10? Well, it goes into it 5 times. So this is 0.5. So 2 times 5 is 10. 10 minus 10 is 0, so there's no remainder, so it's just 0.5. So I can use long division, or I can use a calculator to help me as well. Now, how do we convert from fractions to decimals with repeating decimals? So again, think of fractions as division. So therefore, 1/3. That's the same thing as 1 divided by 3. When I put it into my calculator, I get 0.3 repeating. Now, we could also use long division to figure this out. So I put this in as 1 divided by 3, and I know that 3 can't go into 1, so I know it's going to be 1.0. So I just add that decimal point. So now, how many times does 3 go into 10? Well, it goes into it 3 times. And then 3 times 3 is 9, which leaves 1 as my remainder. 3 doesn't go into 1, so I bring down another 0. 3 goes into 10 3 times, which gives me 9 again, and then 1 remainder. And if I notice, I keep getting 1 as a remainder, so it just keeps repeating itself. So I just keep putting 3, 3, 3, 3. So therefore, I notice that the remainder is always the same. Therefore, it's a repeating decimal. So it becomes 0.3 repeat. Now, how do I work with decimals? Okay, think of decimals as fractions over some denomination of 10. For instance, 0.5 is the same thing as 5 over 10. Now, for every number after the decimal point, I include a 0. So it's 1 and then 1 0 because there's one value. So it's 5 over 10, which in this case simplifies to 1/2. So for every one digit that is included after the decimal point, add 1 0 to the denominator after the 1. So there's one number after the decimal point, so I know I'm going to have 1 0. So my denominator would be 10. And then I place this digit over the denominator, so it'll be 5 over 10. So look at it here, we have 0.13, and we're saying that that's the same thing as 13 over 100. So for every number after the decimal point, we include that many zeros. So in this case, there are 2 numbers. So there's 2 digits there. Therefore, our denominator will contain 2 zeros after the 1, so it'll be 100, which is 100. Then we place this value over the top. So it's 13 over 100. Now what happens if we have repeating decimals? Well, I'm going to tell you right now that therefore 0.5 repeat is the same thing as 5 over 9. Now how do we get there? So for every one digit that is included after the decimal point and is repeating, we add 1 9 to the denominator. So in this case, there's one digit after the decimal point that is repeating. So we're going to include 1 9. So it will be 5 over 9. Now for this one, we have 0.03 repeat, which I'm telling you is the same thing as 3 over 90. Now here's how this works. So for every digit that is repeating, we include a 9. For every digit that's not repeating, we include a 0, right? Just like we did before. So in this case, we have one digit repeating. So we're going to include a 9. And we have one digit that is not repeating. So therefore, we're going to include a 0. So it becomes 9 and then 0. Then we just keep whatever's here, so that's 3, so that becomes 3 over 90. Now this one here says 0.033 repeat. So what this should end up being is 33 over 990. So let's use our rule again. So for every digit that is repeating, we include a 9. For every digit that's not repeating, we include a 0. So in this case, we have 2 digits repeating. So that should be 2 9, so 9 9. And there is one digit that is not repeating, so it should be 1 0. So it should be 990. And then we just keep the numerator here. And then we just keep this value here, 33. And that becomes my numerator. So this is 33 over 990. Now we have 0.003 repeat, and I'm telling you that that's equal to 3 over 900. So again, For every digit that's repeating, we include a 9. For every digit that's not repeating, we include a 0 at the end. So in this case, we have one digit that's repeating, so we're going to include 1 9. And we have two digits that are not repeating, therefore we should have 2 zeros. So we should end up being 900. Then we just keep whatever the value is. In this case it's 3, so it's 3 over 900. Now what if this value here, the non-repeating, what if that value is not a 0? So we have 0.43 repeat, and I'm telling you that that's the same thing as 4 over 10 plus 3 over 90. So we're going to treat this as being separated from each other. So 0.4 is 4 over 10, and this is really 0.03 because we've already included this 0.4. So this will be 0.03 repeat. So we use our rules here to get 4 over 10 for the first part. And we use our rules for this to get 3 over 90. And then we just add those by finding a common denominator. So if not all the digits are repeating, add 1 9 for every digit that repeats and 1 0 for every non-repeating digit, just like here. So that's one digit. So that becomes a 9. This is not repeating. So we end up with 3 over 90 and 4 over 10. If we multiply both top and bottom here by 9, we get 36 over 90. Well, 36 plus 3 is 39, and 90 is just the denominator, so it's 39 over 90. So that's your notes on decimals and fractions. Let's take a look now at the Reasoning with Rational Numbers review assignment. Our assignment begins with our learning goals and success criteria. If we scroll down, we can see some of the questions that are on the review. The first one says, is the set S equals rational numbers closed under addition? Well, we have to decide, is there any way I can add two rational numbers or two fractions together and get something other than a fraction? Well, there is no way to get anything other than a fraction, so we'll go ahead and click yes, it is closed. Now the next one, it says, decide if the statement is true or false. 4 over 7 is greater than 1/2. Well, half of 7 is 3.5, and 4 is bigger than that, so yes, this is bigger than a half. So we'll go ahead and click true. So we'll answer each of these questions until we get to the end. Once we get to the end, we'll click next. This will take you to your before you go. Go ahead and fill out your before you go and then submit your work on Google Classroom.